Hello, so today we will continue our discussion on the thermal properties of solids, and in particular we will talk about the Debye model and what he introduced, so as he explained what happens at very low temperatures. So Einstein's formula at low temperature does not agree with the experiments. In 1912, Peter Debye discovered how to better treat the quantum mechanics of oscillations of atoms and managed to explain the T-cube specific heat. The Debye model treats the atomic vibrations as phonons in a box, where the box being the solid, in contrast to the Einstein model, which treats the solid as many individuals non-interacting quantum harmonic oscillators. The Debye model is a solid state equivalent of Planck's law of blackbody radiation, where one treats electromagnetic radiation as a gas of photons in a box. The periodic boundary condition means that any wave in this sample, e to the ikr, is required to have the same value for a position r as it has for r plus l. So I will have e to the ikr plus l is equal to e to the ikr. This then restricts the possible values of k to be KL equal to pi n, because this is the only way I will have e to the ikr plus l equal to the e ikr. And k is equal to pi over l, 2 pi n over l. It's a result from this KL equal to pi n, where n is an integer. If we are ever required to sum over all possible values of k for large enough L, we can replace the sum with an integral, obtaining summation over k is L over 2 pi integral over dk. In 3 dimensions, it is similar. For a sample of size L cube, k can only take values 2 pi over L, kx is 2 pi over L and 1, ky is 2 pi over L and 2, kz is 2 pi over L and 3. Where n1, n2, and n3 are integers. So here, vector k point now occupies a volume of 2 pi over L cube. Because of this discretization of values of k, whenever we have a sum over all possible values of k, we will obtain summation over k equal L over 2 pi cube, integral over dkx, integral over dky, integral over dkz, with the integral over all 3 dimensions of k space. Now, we need to calculate the density of states in 3 dimensions. We have obtained that k vector is kx 2 pi over L and 1, ky is 2 pi over L and 2, kz is equal to 2 pi over L and 3. So kx can be 0 or plus or minus 2 pi over L, or plus or minus 4 pi over L, or plus or minus 6 pi over L. Same thing for ky, same thing for kz. Therefore, there is one allowed value of k per volume. The volume is 2 pi over L cube in k space. So one value only in 2 pi over L cube. So L over 2 pi cube values is 1 unit of volume. So we have L over 2 pi cube is volume divided by 8 pi cube. Allowed values of k per unit volume of k space for each polarization. Volume equal L cube is the volume of the specimen. The total number of modes n with wave vector less than k is found to be L over 2 pi cube times the volume of a sphere of radius k. Thus, n is equal L over 2 pi cube times 4 pi over 3 k cube for each polarization. Here we find that the density of states for each polarization G of omega is dn by d omega, which is dn by dk, dk by d omega, which is L cube k square over 2 pi square dk by d omega. Debye decided that the oscillation modes were wave with frequencies omega of k equal v times k, not a single frequency as in Einstein model. So here the omega changes with k. With v, the sound velocity taken as constant for each polarization type. For each k, there should be 3 possible oscillation modes. Just in the case of light, it's only 2. 1 for each direction of motion. Thus, he wrote an expression entirely analogous to Einstein's expression, where the expectation value of E is 3 summation over h bar omega of k, nb, which is a function of beta h bar omega of k plus half, which is equal to 3, if I put it in the integral form, 3 L over 2 pi to the cube integral over h bar omega of k, and b as a function of beta h bar omega of k plus half dkx, dky, dkz. Each excitation mode is a boson of a frequency omega of k, and it's occupied on average NB of beta h bar omega of k times. By spherical symmetry, we may convert the three-dimensional integral to a one-dimensional integral. Integral over dkx, dky, dkz is the integral from 0 to 2 pi to d phi, integral from 0 to pi to d theta sine theta, integral from 0 to infinity to k squared dk, which is equal to 4 pi, the integral from 0 to infinity to t squared dk. Here we use that k is equal omega over v, which means dk is d omega over v, where we obtain now the expectation value of E to be 4 pi L cube over 2 pi cube, the integral from 0 to infinity, omega squared d omega 1 over v cube h bar omega, and b of beta h bar omega plus half. Implies the expectation value of E is d omega, g of omega, h bar of omega of this function, and b beta h bar omega plus half, where the density of state for the three modes is given by g of omega, which is equal to 3 L cube k square over 2 pi square dk by d omega, with k equal omega over v and dk equal d omega by v. It's convenient to introduce n equal n over L cube, where n is the density of atoms. We then obtain g of omega. So I will just put, instead of n of L cube, I will be introducing n. So I will get g of omega is equal to this thing, where omega d cube, so first it's equal to this thing, but then I introduce omega d cube equal to 6 pi square and v cube, will be known as the Debye frequency. The meaning of the density of states here is that the total number of oscillation modes with the frequencies between omega and d omega is given by g omega d omega. Thus, the interpretation of the equation of expectation value of E is simply that we should count how many modes there are per frequency, then multiply by the expected energy per mode. We thus obtain expectation value of E equal 9n h bar over omega d cube, integral from 0 to infinity d omega cube divided by e to the beta h bar omega minus 1 plus t independent constant. Okay. By defining a variable x equal beta h bar omega, this becomes expectation value of E 9n h bar over omega d cube beta h bar, all of it to the power 4, integral from 0 to infinity to dx, x cube over ex minus 1 plus t. The integral of 0 to infinity dx x cube over ex minus 1 is equal to pi to the 4 by 15. Thus, we obtain expectation value of E to be 9n kbt to the 4 h bar omega d cube times pi 4 over 15 plus t. So the heat capacity, which is del E by del T, will be n kbt cube by h bar omega d cube times 12 pi to the 4 by 5, which is proportional to T cube. This correctly gives the desired T cube law for the specific heat. Furthermore, the prefactor of T cube can be calculated in terms of known quantities such as the sound velocity and the density of atoms. Note that the Debye frequency in this equation is sometimes replaced by a temperature. H bar omega d can be replaced by kBTD, known as the Debye temperature. So that C, which is del E by del T, can be nkb T by Td to the cube times 12 pi to the 4 by 5. Debye interpolation. In the expression derived above, the heat capacity is proportional to T cube up to arbitrarily high temperature. We know, however, that the heat capacity should give 3 kBn at high T. Debye understood that the problem with his approximation is that it allows an infinite number of sound wave modes, omega goes to infinity. Debye guessed correctly that there should be only as many modes as there are degrees of freedom in the system, and he decided to not consider sound waves above some maximum frequency omega cut off, with this frequency chosen such that there are exactly 3 n sound waves modes in the system. we thus define omega cut off via 3n equal the integral from 0 to omega cut off d omega g of omega. The equation expectation value of E will then become the integral from 0 to infinity d omega g omega h bar omega m beta beta h bar omega plus half is rewritten, dropping the 0-point contribution, the constant term, as the expectation value of E is the integral from 0 to the omega cut off d omega g omega h bar omega n b of beta h bar omega. Let us now check this cutoff if it gives the correct high temperature limit. E to the beta h bar omega is 1 whenever KBT is much higher than h bar omega, and E beta h bar omega minus 1 is approximately beta h bar omega, and we find NB beta h bar omega is 1 over E to the beta h bar omega minus 1, which gives me 1 over E beta h bar omega is KBT over h bar omega. Thus, at the high temperature limit, the expectation value of E is the integral from 0 to omega cut off of this thing, which gives me K beta T, the integral from 0 to omega cut off, d omega g omega. And finally, expectation value of E is 3 kB T n, yielding the Dulong Petit high temperature heat capacity C, which is del E by del T, which gives me 3 kB n, that is 3 kB per atom. For completeness, let us now re-evaluate our cutoff frequency. 3n is the integral from 0 to omega cut off d omega of g of omega, which is integral from 0 to omega cut off d omega n 9 omega squared over omega d cube, and this is a 3n omega cut off cube by omega d cube. And thus omega cut off equal omega d. The cutoff frequency is exactly the Debye frequency over here, because 3n is equal to 3n, so omega cut off is equal to omega d. Now, this is a plot of heat capacity of silver. Okay, the dotted lines are the heat capacity of silver. The y-axis is C in units of calorie per mole. In these units, 3R is around 5.96. Over the entire experimental range, the fit to the Debye theory is excellent. At low temperature, though, at low temperature, T recovers the T cube dependence, and at high temperature, it converges to the Dulong and Petit. Okay, so we see that the Debye is much better than the Einstein. Discussion, and this is the end of this unit. The introduction of the cutoff seems like a successful cheat rather than real physics. We have assumed sound waves follow the law omega equal dk, even for extremely large values of k on the order of the inverse lattice spacing, whereas the entire idea of sound is a long wavelength idea, which doesn't seem to make sense for high enough frequency and short enough wavelength. Experimentally, the Debye theory is very accurate, but it's not exact at intermediate temperatures. At extremely low temperatures, metals have a term in the heat capacity that is proportional to T. So the overall heat capacity is C equal AT plus BT cube. And at low enough temperature, the linear term will dominate. Nonetheless, despite these problems, Debye's theory was a substantial improvement over Einstein's. This is the end of the Debye's model. In next lecture, we will do some exercises.